Okay, please.
All right. So unfortunately, many people are abroad now attending workshops. So offline workshops has started. I found that in Europe or in America, they have offline meetings every week. So when I went to the meeting early June, so there were Prague before. So there were four or five people from Prague, and then some of them got COVID. So Prague is a source of spreading COVID cases. Okay, so today we have Professor Choong Sun Kim. He has very exciting news about distinguishing Majorana versus neutrinos. So he will tell us what's the secret.
Okay,
Okay,
thank you. Actually, now Europe is quite bad. Okay? So hot. And I think there must be difficult because almost all places there's no air condition. That's the problem. Here, even though it's very bad, we have air condition. So that's difference. Okay, let's go on now. So today the title is as shown here. An active neutrino, sub-eV active neutrino is this Dirac or Majorana. Okay, people try to find this Majorana or Dirac by using this neutrino stability decay. Okay, so that's the whole idea of this for a long time. So actually, I think I found some alternative to find this if the sub-eV neutrino is Dirac or Majorana. Okay, this work is with Muti and Sahu.
So are they in Yonsei University or?
No. Actually, when I started this work, Sahu was my postdoc.
Okay.
Now he's postdoc in Poland.
Here at the Poland.
Yeah. Since last year, okay, in Poland. Muti is professor in India. Okay. This is the professor.
Poland? I met one Indian from Poland.
Yeah. Warsaw University.
It's worship. That's a different one.
I see. Okay. Content. I will just introduce short introduction, okay, for new mass and seesaw and Jerome beta I just mentioned now. And then I go to the how we go instead of Jerome beta how we go in an alternative way by using the quantum statistics. And then we got some problem called usually Nogo theorem. They say critical Dirac Majorana confusion theorem. Because of this theorem, people think this theorem, there's no way to go over. Okay, Jerome beta they say is the best. There's no other way. Okay, but I will say about how the picture of this DMCT, and then find there is some hole. There is a way to overcome that. How they overcome? That is the exception of DMCT is by using the back-to-back nuance in some B0 decay. Let's say B0 at rest time decay to mu and nu. Okay, and then back-to-back nuance. Even without seeing neutrinos, I know, like muons coming back to back, neutrino must be back to back. Okay, because let's say the B0 is the rest. This example, or J side is example. J side decay to mu nu. And then neutrino we don't see. For muons, they are back to back. Then I know the neutrino must be back to back. Okay, even I know the size of this energy and the momentum side, everything, almost everything known, even though we don't see that. Okay, so by kind of importing the neutrino momentum or energy, we can overcome this DMCT. That's what I'm saying. And then detailed analysis. Detailed analysis, you don't need to see this paper because my paper give whole details of this. Okay, in my paper, about 30 pages long, the PhD paper give all the details of this. Okay, then how somebody say, how is there something wrong? Okay, actually, last week, there was a guy in China, okay, because I talked to they did whole calculation. They found it's correct. Okay, they cannot find anything wrong. And I just heard from the Chinese guys. And the summary and the spec curve is you don't need. Okay, introduction. As I mentioned, I will just sketch go on like this. Neutrino has mass, okay, non-zero mass. We know that because neutron oscillations. These two guys, Nobel Prize 2015. Now, then how to put the mass there? That's the problem because we haven't found a new R. Okay, so that's the problem. To put the mass usual standard way. So then they try to get by assuming there's new R or some just not with a new R, just neutrons, antineutrino same, and then given the Majorana mass there. That's also possible. So both is actually some problematic because we haven't seen the new R, and this way of giving the mass is not standard way of giving mass, not Higgs mechanics. So those two, some hurdles can be overcome by using the seesaw. Seesaw is actually kind of magic in that sense. Those two questions or some hurdles can be overcome by this seesaw. Okay, there was another problem there actually, because all the other fermions is here, at least something over some around MeV, that range over that, and even 100 GeVs. But now this is something like much smaller than EV now, looks like, even like milli-EV, something like that. So it's something far, far away. Why such a thing happen? Because there must be some reason usually, okay? And that could be accidentally such a thing was possible, but usually some reasons behind. So they think, okay, seesaw, that can be resolved that also, okay? Because of this heavy, unseen the white neutrino giving this so light, this you call seesaw like this. But there are some challenges. Challenges, we need to find this new two or new R, the heavy right hand, such a some sterile neutrinos have to find that. Another thing is new one, which means the base against the right one. This one must be also Majorana. Okay, so what I'm saying, sub-eV active neutrino, we don't know yet it is Dirac or Majorana. But if the seesaw is correct, new one must be Majorana. That's the reason people try to find this sub-eV active neutrino is Majorana or not. So the people try to a lot. Usually they're doing is like delta 2, lepton number 2 violation, and neutrino risk habitat is this usual case. Okay, like some protons came to the neutron and then coming like leptons only, no neutrinos like that. Okay, then if this is only possible, neutrino is Majorana. Okay, Dirac case, nu cannot disappear. Okay, but Majorana case, nu can disappear. Okay, because kind of anti-particles. Okay, that's the reason when this coming like this way, then comes out this is the just lepton number, lepton current give like this kind of thing. This is like this propagator. So and then this is the how it's challenging this try to find out. Okay, now this p slash use goes away because this gamma mu, another gamma. So this goes away. Then nk. Okay, this is just space integral. Okay, doesn't matter. So important things like two mixings here coming from here, and then neutron mass. Okay, this observable of these quantities depending on neutron mass square. As I mentioned just some minutes ago, neutron mass so small, could be even much smaller than 1 eV, 1 electron volt. Then the square of that could be almost zero. I'm saying, okay, this could be almost zero, which means observing this. This neutron after decay is kind of not easy, what I'm saying. Okay, so usually, not only that, they try to depend on scale of this experimental scale and the mass. Okay, then neutron after decay or rare meson decay. So collide searches for this usually the heavy one. This is the light sub-eV electron volt one. So this is all using these equations. So M scale is there. Oh.
So let's say if you observe neutrino-subunit decay, then you can certainly say that neutrinos are Majorana.
Yes.
Is there any caveat?
Yeah. If we see, okay, let's there are now something more than 30 experiments in the world, okay, going on now, and even one in Korea, okay, one in Korea, the experiment they're trying to do this neutron decay. Okay, then if they see that, then neutron is Majorana. Okay, the problem is even you don't see that, neutron could be Majorana too. Okay, because neutrino is actually Majorana can mimic Dirac. They're doing exactly same as Dirac. But Dirac cannot do this. Majorana can only this. Okay. What I mean is, you don't see this one, you cannot say, oh, neutrino is no Majorana. You cannot say that. That's the problem. Anyway, this is experimentally horrible because so small.
So what he says is that there could be no physics effect, even though neutrino is Dirac itself.
Yeah.
So yeah, there are more than
I am asking whether there is any caveat of this statement that if neutrino-less evolutionary decay is, I mean, one can see neutrino-less evolutionary decay, then it will guarantee that neutrinos are Majorana.
Okay.
And that statement is, I don't know whether there is any caveat of this.
There is caveat. Okay. This one, okay, some heavy neutrino too. That can actually depend on heaviness there because now mass is heavy, then it can have a much larger values there, scale. But smaller mixings there. Okay. So depending on where is it, the people try to like something like EV scale or even slightly heavier EV scale. That is must be new physics neutrino, not usual sub-eV neutrino. Okay. Now the new physics neutrino that could also give this kind of things, depending on the mixing and the masses. Okay, that's also possible. But this is not possible by strict standard model. Okay, standard model delta L equal to not possible. This is beyond the standard model. Okay, saying neutrino is Majorana, that is actually kind of beyond standard model. If we say strictly say. Okay, this is kind of thing, comparing this so light or heavy, some less rounded, how that changes. Okay, but this is not my talk, so I don't need to talk you details. This is neutron without a decay. Okay, as I mentioned, same thing previous. When this proton becomes neutrons, so not just single beta decay, but both beta decay, two beta decay at the same time, same place. That's problematic too, because this can happen. Just one some atoms, okay, one nucleus, but not two at the same time. Okay, that is actually hard to calculate, estimating that probability. The calculate probability of some kind of these two neutrons or some protons decay simultaneous beta decay at the same time, same place. That is we call nuclear matrix element. Okay, that is very problematic. And theoretically calculating is horrible. So large error there. But this is, I'm saying, that's just the M neutron scale. That is, let's assume there's some numbers, then we can just know how many is coming up. Okay, this experiment, let's go on. Because this is kind of thing presently. Okay, normal hierarchy, inverted hierarchy means mass ordering of neutrinos. Okay, I'm saying here is we say nu E. Okay, electron neutron is involved here. Okay, that is actually the lightest. Actually, could not. If it's inverted hierarchy, that could be slightly heavier. Okay, because in this case, something nu 3 actually lightest in inverted hierarchy. So nu 1 is lightest to normal hierarchy. Okay, so normal hierarchies usually can just go almost zero like that way. Okay, but inverted hierarchy slightly larger. So if
what kind of isotope do we use for this neutrino-less double decay?
pardon?
What kind of isotopes do we use for this zero new double beta decay?
Oh, what kind of isotope that I show here? This tried, but here, but this is not my talk, okay? I want to go my part. So just sketch go on, okay? You can go like nuclear battery decay. There are so many papers, okay? So okay, experimentally, this going to go this way. This is like
You mean,
two beta decays like coming.
you said that it's rare that the two of the protons will decay simultaneously to neutrino.
Yeah.
So is it not possible to find out typical kind of isotope where this probability is high?
I mean, that's the experiment that they tried to calculate.
That's a variable. Probably you are.
Yeah,
this is there to try and calculate for each element, okay? And there is,
we have Amore experiment.
Yeah.
Which uses
In Korea.
Molybdenum.
but
Germanium, molybdenum, those are all the popular ones.
yeah. But I mean, a theorist, I say, I mean, that has large error. That's I can say that. I mean, the value itself is depending on whole nuclear structures. Okay, so let's go on because that's not important to me. What I'm saying was normal hierarchy is possible, and even that is more now possible because this super K, okay, in Japan, they did the whole this observers, and then they classical analysis to find the orderings, and they find looks like normal hierarchy is more better than this inverted hierarchy for minimum classical. Okay, so looks like I mean not definite answer, but more or less normal hierarchy is better than inverted hierarchy to fit in all the experimental data, which means there's large possibility you cannot measure that. You cannot by using this one because they could go down and down. Okay. Now presently current bound going down is like they say going up here, but that's huge now detectors using tons. Okay. Now that makes 100 tons. I mean, it's impossible going down like huge and huge like. Anyway, I mean to me, okay, I want to find some other way. Okay, that's what I want to say today. Okay, this is some sterile, heavy sterile neutrinos. Okay, like this possible. B plus goes to pi minus L plus L plus. That's one number 2. I mean, delta equal to this one. Okay, 2. If mass, this n, mass is between MB and M pi, then could be resonance decay. Then this can give shooter. So we can find that. That's the way to using the resonance structures. Okay, now let's go on. Okay, this is not my part. Okay, now this is my main talk. Okay, now main part. Now, I said how we go over this delta L equal to, that is M nu square. Okay, because M nu is so small. If M nu is so small, M nu square is much experimental, almost impossible to overcome that. How we overcome this? There are people tried many ways. One is the neutrino Casimir force. Okay, just like usual Casimir force. Okay, this is the possibility. So small mass maybe fail. You may fail this observed experimental this. So you need some other way. Other ways, one of them is like neutrino Casimir force. But the problem is this result is actually M nu square. Okay, neutrino mass is coming from this, okay, kind of virtual, this neutrino coming like this way. So neutrino mass is there. So this is again, is impossible to overcome. There's another thing actually, people talking. EDM, neutrino EDM or MDM, okay? Like in the case of this Majorana case, it's 0, okay? But Dirac case, maybe non-zero, but that's M nu square too, okay, again. So always you come out, try to overcome, you try to differentiate the Dirac from Majorana, then you come out M nu square. Now neutrino mass so small, experimental harbor. Okay, so I'm just saying alternative way. Alternative way is to Jerome beta is quantum statistics. Okay, let's neutrino Majorana. Okay, neutrino Majorana, then let's use quantum statistics. Final state coming out nu or nuba or nuba. Okay, I mean 2 neutrino come out. There's 3 possibilities. Okay, now these 2 nu or nuba case, no difference between Dirac or Majorana. Okay, because Dirac 2 you have to anti-symmetrize because as fermionic, the Dirac fermi statistics making this Dirac and Majorana same, but only nuba case different. If it's Dirac, you don't need to make this anti-symmetrization. I mean, I just said the delta equal 2, like nu can disappear. I said, okay. This is only this. Okay, this we want to see that. Okay, so anti-symmetry for only Majorana case. The best one would be like this way, L minus L plus nu nu bar. This is the case you wanna approach on that. The preference goes L goes to mu, because electron usually has the shorter reconstruction, the decay length. But muon is much easier to reconstruct. So I said mu minus mu plus nu nu bar. That's I'm going to say today. Okay, but you can extend some others too. Okay, so decay mode is B0 was to mu mu nu nu bar. B0 bar to say. Okay, so experimental is bell2 actually. Now bell2 is, if you know the bell2 actually, B0 is not produced at the stand, at rest, and moving. Okay, they have like asymmetric factories. E plus E minus coming not the same energy. One E plus actually slight small energy, E minus large energy like this way. So B0 is moving like this way. But we need B0 arrest because this is missing. Then we don't know which is missing. Only way when this is rest, then we know that missing or not. So we need to rest frame, B0 rest, and then we want to look at this. So we need some hadronical reconstruct the other part. Then some efficiency actually quite reduced because present bell2 designed luminosity is about 10 to 11, 12. Okay. Then with the fully reconstructed B0, that is about 10 to minus 9 B0s. Okay. So like something 100,000 times reduced. So we have not many B0. So that is the problem here. But let's go.
Confusing the Polish notation. So Majorana means nu bar equal to nu.
Pardon?
So Majorana means nu bar is same as nu.
Yeah.
Then the distinguishing nu and nu bar is not there for Majorana neutrino.
Majorana case is the same. We have to anti-symmetrize it. Because E comes out, we have to anti-symmetrize whole the matrix element. When you calculate this branching pressure, anything, you have to anti-symmetrize same particle
Okay,
come
so
out.
for Majorana, nu bar, all the same, right?
Yeah.
So just one state.
Yeah. But Dirac,
For Dirac,
same. Because this is nu bar. Even Dirac same. So there's no way to distinguish this one.
and then for Dirac, we only have a nu bar final state.
No, final state can come out. I mean, somehow just nu or nu bar, anything could come
I
out.
mean, Dirac case, what you know is that this is a weak process, so so nu and nu bar come out, not nu.
Okay, you are saying it's a lepton number, something like that way, okay?
Yeah.
But I will say just final state coming out. If it's nu or nu bar, how distinguish that? Okay, how it produced
I mean,
new
we know
physics.
that for Dirac, we have only nu bar final state, is that right?
Depending, if there's no lepton number from start. Okay. No lepton numbers from start then.
I mean, Dirac means there is a lepton number conservation.
Yeah. So from start,
the
there's
final
no,
state must be nu bar.
if we start like no,
And then for Majorana, I mean, there is no distinction between nu and nu bar, so all those three states are the same. Huh?
no. How about the left from start is lepton numbers there, E gamma like that.
Sorry?
The lepton number is there, one, start from one.
Yeah, no, it's saying initial state is E minus gamma, let's say.
E minus gamma.
Yeah, then you have lepton number 1 in the initial state, right?
Okay.
Yeah, but what's the final state?
Yeah, I don't know.
No. I I want to show that. So what I want is the
Probably this is some confusion between notations.
Yeah.
Okay.
Okay. This is what I'm saying is at final state coming like this way. I don't care about how initially like this way. Final state coming out this way, then we cannot distinguish from Dirac or Majorana. But this one we can distinguish. That's what I'm saying. That's good because Dirac case nu bar is always coming out. Okay. But if there's a Majorana, you can distinguish. That's what I'm saying. Okay.
Okay, probably right.
Yeah. Considering visual goes to like this way, put the whole momentum like this way. P1, P2 is the important here. The other is minus perfect. And then Dirac case, matrix elements just P1, P2. I just ignore the other two. Then this is that. For Majorana case, we have to anti-symmetrize that because this is now just like electron coming out. Okay, we have to anti-symmetrize that. Without that, then whole this is wrong. Okay, because of that kinematically, like same electron cannot come out because of this anti-symmetrization. Okay. Anyway, this one, second one, is not coming from heliocentric flip. Okay. This second one coming from prime six momentum exchange. Okay. This is momentum exchanges P to P1, not heliocentric flip. This is perfectly possible. There's no suppression at all. What I'm saying, second one, which one is just momentum exchange there. I'll show the diagrams later. This is perfectly okay. No M over E there, suppression. Okay. Now the difference between this Dirac and Majorana, making sure that there are actually two terms coming in. One is coming with direct term minus exchange term. Like this way, half of that. The other is like both these two coming from interference. There are two terms. So we have to consider. Okay? So this interference term actually is M nu squared. In the case of which I said visual goes to mu mu nu nu case, the diagram is this one actually. And then interference coming these two, heliocentric flips here. So this M nu squared. Now, the previous one, there's second term and first term actually. So this one is, we know that M nu squared. Now this one, direct minus exchange this squared. Okay? This term. In general, need not be same, but it could be same too. Okay? This is the depending on models. Okay? Depending on models, I will show at the very end this the equal case too. But usually you don't need. I mean, accidental could be equal, but in general, you don't need equal. So this is it. The problem is, even though not equal, if integrate, it's come out same. Because now once integrate is now this dummy variable. Same. Because now I just hold the P1, P2 there, they're same. No difference at all. So even though there is some differences, once integrate out, same. But you have to integrate because neutrino is always missing. Neutrino is actually in experiment here, visual, the problem here. I just go back. This one, you can see this one only. This is missing. Two neutrinos is, in the case of usual experiment, neutrino just goes away. Which means in phase B, you have to integrate out to get the final state, the branching fraction, anything. So the problem is, even though this is the case, not very useful because the neutrons disappear invisible. We have to integrate out, then disappear, then come out M nu squared. That's the called PDMCT, practical Dirac-Majorana confusion theorem. Okay, practical Dirac-Majorana confusion theorem means Dirac and Majorana. If you do the experiment, even though there's some difference, if you do experiment, no difference. Always come, no, there's difference, M nu squared. What I'm saying is so small difference. Okay, so this called say no-go theorem. There's no way to go over. Okay, this is kind of generic showing. Okay, this I don't say this is some case. Okay, I mean you don't need symmetric Dirac case, but Majorana case must be symmetric. This is E1 over maximum, E2 over maximum. They must be symmetric. This you don't need, which means, I mean, even though, so this is very important. If we can measure neutrino, okay, neutrino is not invisible. Let's say neutrino is, you can measure it from experiment, like muons. Then you can distinguish easily. Because, I mean, interaction different, okay? So you have like all distribution different. You don't need to worry about it at all. So in the case of if you can measure neutrinos, you don't need to worry. But problem is neutrino is technically impossible to measure it, which means you have to integrate out whole neutrino phase space. Then this is disappearing, different disappearing. You got M scale. This called Dirac minor confusion cell. Okay, called Dirac minor confusion cell. DMCT. From now on, I usually call DMCT. That's Dirac minor confusion cell. Okay, this is coming out M scale. Only interference from sub-I. Okay, now this was first said was Kaiser 82. Okay, this is about 40 years ago. 40 years ago. Said, okay, practical means even though there is difference, but difference so small, you cannot measure it. You call practical Dirac confusion theorem. He said theorem, but when he did this, not the theorem actually at all, because theorem means have to be general. But he did only simple one case, which means he didn't do no general proof, no independent process, or no observable independent observables. He did only observable because everything is disappearing. He did observable, that's branching fraction. That's all he did. And the process was actually Z goes to nu bar, or E star, gamma star goes to nu bar, like that. Okay, so that's the not general process. Only some kind of one process choosing, one observer choosing, and then coming out there. Okay, that's the problem. So I want to show that after this 1982, how this is processed. Okay, 82. That's first I mentioned. 0 means starting. Okay, and then up to the 2018 means they tried to overcome this from slightly different processes. Now, as I mentioned, the process independent not done. They did only this kind of processes. They did only total branching fractions. They did. So not observable independent also. They did only that kind of things. They also did within standard model only. So non-model independent they did. Okay, so whole thing was like not model independent, not process independent, not observable independent. They did. Every time they integrate out, then come out disappearing. They didn't know at the time why this was going away. So they tried to do it. Again, E plus E minus K plus, this was now 2 by decay, now 3 by decay. Even though 3 by decay, same thing, you cannot measure anything. Let's say K plus was pi was nu bar. Now K, let's say K is standing here, change the pi, and then neutrino disappear. Where neutrino, you don't know any information neutrinos. There's no way to get any information neutrinos, which means we have to integrate out. So we got same, exactly same thing. All others are same. Okay, this is excited state of nucleons from ground state, and then this some are slightly different interactions, but all they try to overcome it. So they try to something strangely, like this way, all the time. Okay, but they confirmed always DMCT. Okay, 40 years going this way, now they realize this must be correct. There's no exception, they say. Now, then why this is correct? They try to find so much different ways. Okay, but all the time, that is not the answer. That is not the answer. Okay, okay. So this is now discussion on this PDMCT, okay? I don't need to give whole details, but anyway, I just give one or two. But this is actually not theorem at all. As I mentioned, no model independent, process observer independent, could be so-called this theorem. All the process shown was full integration of the momentum missing neutrinos. Okay, so they did total cross-section like this way. Okay, now what I'm saying here, as I already mentioned, this theorem can be overcome if energy or momentum or something neutrino information we can infer or measure or some deduce. So we get some distributions, not total integrals. Okay, so we get information used there. Then we can do it. The way to do it is this one. The best, I drew just one diagram here. Okay, this picture here. and then mu mu nu nu, something like that. Okay, mu plus mu minus nu nu bar like this as example. Now visual rest. This is rest. I know this is back to back like this way. I mean mu was like this way. Now even though I don't see that, this must be back to back.
So it doesn't have to be. So you just select a back-to-back no event, no event, right?
Yeah. I choose only visual rest frame. Mu is back to back. That's only I choose.
So how many of them can you?
Oh yeah. I mean I will show at the very end the branching fractions. Okay, that's the. I mean, how many would it be?
So you see, so basically you are saying that so without integrating over, you can distinguish.
Yeah.
Okay, so that's okay. Yeah, this is going to true.
Yeah. Because you don't see. I mean, without knowing
That's
this.
not against the practical DMCT.
No, not
Practical
against.
DMCT means that after integrating out,
Yeah.
there's no way.
Yeah.
But you are saying then, okay, we don't have to integrate.
Yeah. I mean, the problem was they couldn't find it this way. And this was the kind of magic.
Yeah, the practically, practically probing the distribution would be very difficult.
Yeah. Almost.
Again, practically after doing all the numerical simulations, you may get.
Yeah.
Okay, go ahead.
Yeah. Anyway,
Okay.
you say that is so small. Yeah, that must be
Yeah,
small.
maybe, but that has to be checked.
But this is not mu square dependent, the problem.
Yeah, of course.
Okay.
This is.
Yeah. This is not mu square dependent. In the rest frame of B meson, then I know E nu must be like this way. Okay. This is just E mu. We know that. Then calculable. And this is almost momentum with the two because neutrino mass almost masses. Okay. So I know neutrino momentum is also this one. Okay. Only unknown thing is this angle. This angle is unknown. Kind of this angle. Okay. That's unknown. All others are known. Okay.
So the angle is what?
Angle between muon and the neutrinos.
You have two mu's.
Yeah. So I choose
Angle
mu plus.
minus-
I choose mu plus and the other neutrinos like this.
Okay, then the angle. So in angle theta, it can be nu or nu bar.
Yeah.
I don't know which one.
Yeah. But anyway, even though you don't know, I can bookkeeping. I can because when you calculate, you can put there. Doesn't matter, and you can integrate out. Okay. This is
Integrate out what?
integrate theta
Integrate theta, not T.
because neutrino. This theta is unknown thing. You have to whole
Okay,
region.
go ahead, yeah.
Whole region of theta should be integrate. That's it. Okay. Oh, no. This was second one. And another people said, okay, mu square must be correct because this must be smooth changes. When mu goes to non-zero, okay, Dirac and Majorana could be difference. Now mu goes to zero, there's no difference between Dirac and Majorana. Okay, all the same because there's only two degree of freedom all the time. Okay, so now when mu equal to non-zero, mu equal to zero must be like this smooth limit like this way. That's what they say. No, that's actually not true because statistical properties, okay? Statistical properties of particle does not depend on actual mass, but depend on spin actually. Okay, so in the case of neutrino, which mass is let's say very small, point to all the time say 1 and then 0. This say, oh, this must be all the same. No. This is degree of freedom 4, this 2. There's kind of quantum jump. Okay? So when this mass is so small, this every details property must be same. That's not true, actually. Okay? This is kind of jump there. There's no smooth limit. Okay? Distinguishability, okay, also distinguishable, indistinguishable, there's no intermediate state. This is also kind of jump there. Now, another thing people say, okay, they say, because when you do the nu-nu-bar interchange like that way, there must be suppression, velocity suppression. That is the origin of this DMCT. They say, people say, okay? When I talk, they are saying, many people say that. Then I try to explain them a lot. Then they say, wow. He said, I actually understood that. At the end, very end, because I'm saying, I already say that. The second diagram, which is anti-symmetric, the diagram is from the momentum exchange, not from the velocity flip at all. Okay? They say the second diagram is actually come velocity flip. So that only first diagram and second diagram, there's nothing. They're so small, they say. Okay, that's what many people say. No. What I'm saying is this is perfectly possible without any suppression because momentum exchange there. I'll show that at the very end. In the middle, I show the diagrams. There's no such things. Okay? And this DMCT is coming from, not coming from second diagram, but coming from interference. That interference is only coming when you fully integral. Actually, they did full integral all the time. When they showed all the previous papers, I showed that like 7 or 8 papers there. They did because they cannot measure neutrinos. They just all the time integrate out, and then they got the result. Okay, there's another thing. If this is for this so long because I have to some others. If you have a question at the end, I'll give this answers. Okay, another page space this. Many people say this about. Okay, now this new physics, but as I mentioned, this, direct and exchange did not be same, but the could be same actually. The special case, this fermion case, could be same. The other case is that this could be plus or minus like this way, depending on some models, okay? So beyond the standard model, actually it's possible. Not just standard model, beyond standard model could be equal.
So what is on your B and C?
What is the BNC? Oh. This is B is the 1, 2, and exchange is plus. Minus the C. Equal in like this way. Special scenario is
in the standard model, what you have?
Standard model, you don't need to say. Depending on decays. Okay? Like it's decay of this.
So you mean say
That goes no.
So new physics model, we may have case B.
Yeah. Okay.
Why?
This all details of this.
Physics is dependent.
Okay.
But it doesn't. You don't have to say this. So we stick to the standard model.
Yeah. I don't need to say that. The reason I'm saying is I want to go this whole region. Okay. This is now choose process. Because scatter involving 2 neutrinos at the end. Okay. Are the tormentor nunuba measurable or deducible? Okay. No. That's the usual case up to now. There's no way to measure it. So you go this way. And then now, as you just said, there's no new physics. And then go this way. Okay? That is, people said, comply with the DMCT. Okay? But there is quite a large area, a large possibility of this one. Okay? Beyond the standard model and the possibility of some deducing neutrinos. Okay? People know what people think about this. They just go this way all the time. Because once you go, people going that everybody follow the directions. That's the way going there. Actually, this was the 0 was the Kaiser, I'm saying. The second one, this one, new physics was then actually just after that, Rosen did. Actually, they showed the previous pages. The new physics, you can actually distinguish. Okay. And Chow and
do you know what kind of new physics they are showing?
Oh no, they didn't do it. They just model independent.
Okay, so that they just mentioned the possibility.
Yeah.
Which is
Okay. Now another thing here. This one. I want to say this one because important. Okay, this one. Chabra and Bauer. This guy was first, 1990, after about 10 years later. He said first, if a neutrino is measurable, you can distinguish, he said. Okay? All others just they did without assuming this neutrino can be somehow measurable or somehow can be observable. They never thought about that. They just did integrate out, all come out. But this guy first, no. If we can do it, you can distinguish.
so it's the same statement. You made.
Yeah. what I'm now statement is
So
actually.
I mean, basically, DMCT is not wrong. So you have another way to distinguish Dirac and Majorana.
Yeah.
I mean, it's a too strong. It's a too strong statement. DMCT was wrong. No, it was right. Only after integrating out the final state. But there is a way not to integrate out.
Yeah.
So this is another process.
Yeah. That's probably correct argument, statement.
I mean, it's confused. I mean, if you mix them up, the people would confuse.
Yeah. Okay. I mean,
So anyway, as you mentioned, the interference gives n square.
Yeah.
This kinetic
Yeah.
So in the practical case, integrating out,
Yeah.
that gives only the difference. But
Yeah.
you say no. We have to measure the
Yeah.
signals. And then
Yeah. As this
So
guy
that's the
mentioned.
statement.
As this
So
guy
that's the
mentioned.
92 they
Yeah.
mentioned.
If neutrino momentum can be some way measurable,
Oh.
observable, reducible some way.
So they did some practical, say,
They didn't do anything. They said that.
theoretical
Yeah.
statement.
In the paper in the middle like that, they say,
Okay.
let's say they do integral, and then they say before integral they say, now let's assume neutrino momentum can be measurable. Okay? Then you
So then, this is another issue. I mean, then, so then this is another practical issue, whether it's a real experiment. Can we measure? Yeah.
yeah.
How precisely we can measure?
Yeah. But that's depend on the experiment now. The experiment always,
Yeah,
goes
sure.
progress
Maybe,
and
yeah,
progress.
Really interesting. Yeah.
Yeah. Okay. Now let's go to back-to-back muon case. Okay. Experiment observable except this exception to DMCT. As I mentioned here, like the back-to-back muons. Okay. That's actually back-to-back neutrinos too. Same. Okay. This is the diagram. Actually, there are two diagrams. Like this is non-resonance and the resonance diagram for the mu case. Okay, this a bracket like this is just put the for bookkeeping. Okay, this is just bookkeeping. Okay, you don't need that, but this is like this way. And now we don't need to worry about this one. Let's consider only this non-resonance case. Okay, now with this minor case, we have to minus here, anti-symmetrize that. There, please look at this one. This nu bar here, nu bar, P1, P2. Okay, so this nu mu, this one P1, let's now change to P2. This one, there is no suppression at all. This is perfect second diagram, perfectly partable. There is no M over E suppression for these diagrams. Okay, so people say, as I mentioned, like velocity flip is the origin of the DMCT. That is wrong, actually. Origin is actually because you don't measure this neutrino momentum. You have to integrate, and then you hit this coming up from interference. That's correct answer, correct saying. But many people say that. Whenever I say that, people say, instantly they say, oh, because of this velocity flip, that's the source of this DMCT. That's many people say that. But second diagram, there's no such this suppression at all. How I know that? Oh, this is just bookkeeping, okay? Because minor case M is same, okay? But still, in order to calculate, I have to just put the like bookkeeping and then calculate. If you don't know that at the time, you have to integrate. Okay, that's difference. Okay, for totally unknown, that's experimental. Theory, you have to know that because you have to calculate that. Then you have to put all the bookkeeping like this way, and then you calculate that. And if you don't measure it, you integrate. That's what you have to do. So this second one is not velocity flip, it's momentum exchange. There's no suppression at all. Okay, now kind of Gedanken experiment. Okay, this one, let's say P1, P2 is the same, coming like this way. Okay, which means like electron coming, Mueller scattering, electron coming like this way. Actually, that's not possible. Okay, because electron same, it's not possible to come in collinear like that. This would exactly same for the minor case. Okay, minor case, this collinear must be 0. But Dirac case may not be zero, okay? It could be zero accidentally, but you don't need, okay? So we did actually calculate. It's coming out for linear case for Dirac, minor case zero. For Dirac case, this momentum of this one coming out like this. This is one of form factors. This m nu square, okay? Not m nu square, I'm saying. But the problem here is, so which means the difference may not be m nu square. The problem here is, this is kind of end point of phase space, okay? Not middle of phase space, okay? This kind of collinear coming out, that is end point of the phase space that usually at end zero, okay? So only difference could be if there is. How zero approaching to zero, that difference, okay? Dirac case, the minor case, both become zero because of minor cases because matrix zero, Dirac case because of phase space at end point. So there is a kind of problem at here. So I want to find out the more general phase space, more frequently coming out, not like end point of phase space. That is, I'm saying back-to-back muon case, okay? This case actually quite a lot because muon momentum can be a lot, okay? They're not just a single phase space, some point like that. All this one, theta could be anything, okay? So there are, this is a lot possible, okay? Only possibility is some kind of suppression like muon comes back to back like that, okay? That is some kind of suppression. But there's no other phase space suppression, no symmetry or any dynamics forbidding this kind of thing happen, okay? This could happen all the time. So in this case, as I mentioned already, neutrino energy is nonsense. Because neutrino energy is nonsense, momentum size is also nonsense, okay? Now, m nu, that is nonsense, okay, measurable things, and mu is measurable things. All the phase space relatives, nonsense. Only unknown things like this way. These two lines, angle between these two, that is unknown. Okay, so we have to integrate the angle. That's all. There's difference. There are a lot of things they are unknown, except just one single unknown things. Okay, so because of this, we just integrate for angles. That's why I want to do it. Okay, so this is usually, we got it at end, d gamma over the muon n square, and this sine theta is the angle, which I will just define very soon. Okay, this is another important thing. Velocity consideration. Now, Newton mass equals 0, then velocity and chiral is exactly the same. But because we are talking Newton mass is non-zero, okay? There is velocity and chiral slight mixing there. The mixing is usually coming out, okay? Positive velocity usually should only right-hand chirality, okay? But there is also possible small m of e suppression of chirality, left-hand chirality too. But this is so small, okay? So I'm going to just ignore it because m of e is usually, so small in the case of our experimental point of view. Average of E nu is kind of 1.4 GeV and 4 of this B0 mass, okay? Then this is zero, neutron mass is so small, okay? For muon case, actually that's also so small because muon, the mass not coming pion decay. Pion decay case, okay, which I'm just next page. Pion decay to mu case is actually, muon is so heavy. Okay, m of e is almost order 1. So we have to do the, not just like this way, we have to even part left, right, both, okay? So this diagram is actually 4 diagram comes out. Plus, minus, that's 2. There's 4 or plus 2 possibility of that. So 2 by 2, 4 diagram comes out. But experiment I found, actually, there's maximal parity violation and CP conservation actually come out. This was long ago at the experiment. I will show the next page anyway. This was they did, okay? Pion, what they did is pion is rest, okay? They bring pion rest, they produce pion, and then at the end, pion rest like this. And the pion spin that's like scalar, pseudo-scalar, but spin is 0, then we can do all the possible, which I mentioned, like this, and this also possible, like this way. And they did whole possible, like P and C and whole CP like this way, and they come out only this two possible, which means this is actually weak neutral current, actually. Neutral current, only left hand is involving like that, okay? That was before that, there's no one know that, okay? This was know that, wow, this weak interaction, in the case neutral or charged interaction, there's only left-hand interaction is involving that. That was found from here, okay? Now, very same thing here too. These two is actually doubly weak interactions, weak charged interactions. This is what I'm saying, okay? Doubly weak charged interactions. Mu nu coming from just like W interaction there, vertex with W. So interaction point, chirality actually is fixed at the end because we know the interactions. But once produced on the going propagate, then there's mass eigenstate. Then actually mixed is produced nu L become nu L and nu R at the decaying, like when you propagate. Okay, so that's the we have to do much more careful to this equation solving this one. Okay, anyway, but this one is just like this one, just simply one diagram, not just two diagrams, because we can ignore the other one. Then this is it. Now I just put the angle theta. Let's put the theta is like this way, mu plus and nu bar. Okay, this is in the Dirac case. We know that. Minor case, I mean, this all same, but still I can put as a, for the calculation wise, I can put the bookkeeping. I can put that. I can put it. Okay, and then later I have to symmetrize because unknown things. Anyway, now theta is like this way. This is the case of decay of B0 at rest frame, nu mu nu nu. And then because spin 0 here, this one, this would be come out. In that case, it must be 1 minus cosine theta square like this way, okay? Because this is, you cannot go on other way. Now, minor case, as I just mentioned, even though I don't know, this is just nu m, but still I can do that, okay? Because the bookkeeping is nu, but because momentum exchange, okay? This must be P1 and P2, same section, like this one. Then, this one is theta, cosine here, 1 minus cosine theta, square like this way. Then the other one, minus of this one, that is now square, that must be plus 1 minus cosine pi minus theta square. Now plus, there's actually interference term, m nu square, okay? Now, this goes to 0, then this is very important. That is DMCT, okay? If we integrate out, actually this usually truly phase-space integral, then this goes away. But if we just choose some peculiar, smart way, then that integral will be same. Okay, full phase integral should be same, but I mean just a special kinematic integral need not be same. Okay, then this is not important because this might be large. Okay, that's what I'm saying. Still, theta is unknown experimentally, so you have to integrate. Okay, now this is the Dirac case. This is Majorana case. Okay. So large difference. Now, neutrino is missing, wholeness. So we don't know this angle. Doesn't matter. So you have to integrate. Okay, the angle theta is completely unknown, so you have to need to integrate out. Then we know that this much larger branching fractions. Okay, for special this kinematic case. Okay, back-to-back neutrino case. Okay. Back-to-back neutrino case. I know the others, not only moment, not only branching fraction, but energy distribution of d gamma with d e mu. Okay, that is a d gamma with d e nu, same thing. Okay, that is measurable things. We can integrate the part, not full. Okay, integrate the phase space. I just do it that way. Then come out huge difference. Actually, this is about 20 times difference. Look at this. Actually, this is about 20 times. So 20 times means true level is okay. You don't need to worry about some negative corrections. As correction cannot give 20 times larger making that. Okay, so I just did simply true level calculation. Then the difference is and then compare the experiment. That's what I'm saying. Okay, in the case of, this was because of the Professor Chen asked a long time ago, then I added that, but if the question come out, I say, okay, let's go on. Because in my case, everything is now given that. Okay, now detailed analysis. Detailed analysis is actually shown in my paper. Okay, now look at this. Archive is actually June, end of June actually, but we submitted July, early July last year. And this is, if you look at this one, is early June of this year. So it looks like about almost 11 months has passed. Okay, this was because I mentioned this DMCT was so difficult to explain to people. Okay, there are there are 4 referees involved. First 2, one just say, okay, this must be correct. So they accept, almost accept, change this part, okay? The other one says, this must be wrong because this must be smooth, as I mentioned. And the DMCT must be correct all the time. There's no way to overcome this, he said. So because of that, even though he cannot find anything wrong, there must be wrong, he said. There's no way to fight against that because he said, there's no way to find anything wrong, but there must be wrong, he said. I mean, I cannot fight against him. Please say, where is wrong? And then they send to CD. Same thing happened again. C, accepted because this must be correct. And D, same. This cannot be correct because all the time, this amnus there's no way to overcome this. Because 40 years they're going on. And then again, that was end of last year because we submitted the early July, and then this end of the December. Then we sent the email to this PRD. Please do not send again. You please decide from the whole this referees. Just look at this and read which is more reasonable. You decide, not just send again to EF like that way. Then said, okay, we'll not send again, but we'll send to now this PRD LPR board members. It was 30 people actually. They sent to that was January 5. And then they decide June 4. This must be correct. They accepted. Okay? They did whole possible everything. They cannot find anything wrong, and they accepted. But still, I said there might be some experimental, some theoretical wrong. But now, last 2 weeks ago, Chinese guy, they did calculate. They did whole day away. They find there's nothing wrong. They got exactly same answer at the end. Okay, so now I'm perfectly okay because not only me. Okay, the Chinese guy, they said they correct. Okay, anyway.
So editors explicitly say that the calculation is totally right.
No, yeah, they say that. There's.
How do they know? They are not expert.
But they try to find
So
everything.
50-50, yeah, always. Then how do they judge?
No, they spend about 5 months.
Okay.
Yeah.
Poor editors.
From January 5 to the June 4, which means about 5 months. Okay, they spend. They say there is no any scientific issue here. Everything is correct. They said. Okay. Anyway, I mean, still, if I try to say, then almost people said, no, they must be wrong, because this must be amnuskia, they say.
No, that's not correct.
Yeah. I mean, this historically they did. What they did is always they did integral, because this unseen. I mean, there's no other way. They have to do it. Okay, that was the problem. So whole details actually in my paper, but anyway, I just show just a simple few questions. Okay, this was I already showed a pretty long time ago, some time ago. This was now quark level and the resonance for this one. This for quark level for in the case of the Majorana case must be symmetric, anti-symmetric this way for resonance. Okay, I mean, this is all this the electronic current and hadronic current like this way. And then we put everything. This is the for bookkeepings like this way. This whole only for bookkeepings. Okay. I mean, you cannot write that, but when you calculate, you need that. So that's the you have to put it there. Okay.
Then the calculation, I mean, you just pick a right-handed guy, so this distinguishable.
I mean, we did whole everything in there. Okay.
I mean, the bookkeeping means that you put PR, right-hand projection.
Yeah.
So it's
Any-
injection is fixed, right?
Anyway, we did. Okay. What I'm saying is
I
that
mean, okay, I am trying to say what you did.
what you did was all these calculations.
Okay, so probably we are talking the same thing.
Yeah. Okay. Okay. Anyway, what I'm saying is, in the case of this, for the resonance case, we have like usually two form factors. Okay, this one and
Okay.
the prime is actually for the interchange case. For the non-prime is the Dirac case, no primes like this. But the minor case, we need also prime like this for interchange. There's F plus and F minus. For the non-resonance case, we did whole general structure. Let the Lorentz invariant general structure. Then we got the three form factor like this. And then this is actually usually dominant form. This is something CP related, but this is usually small. So we just use this one only and we calculate. Okay, and then this is just the kinematics, okay? How angles are defined in the case of like a general case. This is not back-to-back case, general case. Visual here going like two, like this, the momentum of QM or this muons and neutrinos, and then here back-to-back, and the rest, in the rest from this muon, the central mass, neutrino central mass, angle theta m, and this the two planes angle theta phi like this. Now, actually, this theta n and this phi, this is actually unmeasurable things usually, okay? That's unmeasurable things in the general case, what I'm saying. So in general, if we integrate this part, then we have to get the PDMCT actually, okay? I mean, neutrino related part, we just integrate out, then we'll get the recover DMCT. That's related to this. This is known things. Missing mass square is actually measurable things. Okay. Only unmeasurable this angle and this phi. So if this integrate these two, we have to recover DMCT. Okay. We did actually. We showed that this DMCT is confirmed actually. So this integrate out, only the other part is coming out, and then M and D coming out, this M nu square. Okay. So we actually confirmed DMCT. Okay, in case of neutron observed, unobserved, we have to integrate this theta and the phi like this way. And then in the paper, they show all the everything. Okay, you can see that every time here and there, always coming out from the other way. Only non-canceling is this M nu square. Okay, this part. So we got before just integrate only this unmeasurable things, and that we got M nu square. So we confirmed actually DMCT is coming from integrating these invisible neutrons. Okay, and then the kinematics is so simple now. Once you know, now go to back-to-back is from the general, the back-to-back is simple. You just choose such a frame, then almost everything is known things, and then these angles are all the known things. Only this theta, the theta was previous I defined this mu plus and the nu by like this angle. The theta was now here coming like theta m. So cosine theta m is sine theta m. So we come like this is the neutral part, which you might say, which is unknown things actually. So this sine theta is unknown things. So we got the d gamma, d m means Dirac minus. So this vectoring is only back-to-back kinematic case. This is measurable quantity, and let's assume this is also measurable, then this is it. But this unmeasurable, we have to integrate out. So this is the case. And then the result is actually coming out. For this, we see the difference because I want to always difference. It is DMCT or not. Okay. This is for the back-to-back. for the now measurable the neutron energy and like angle theta, let's assume measurable like that. Then this comes like this. And then minus. Okay, let's say this is mu square or not. This one, this is actually 0 comes out. This one, here, this doesn't go to 0, mu square like this. Cosine theta times this one. This is not mu square. Only this is 0 when cosine theta means sine theta equal plus minus 1. At the time, this is same, actually. Actually, that is the case. We already did velocity analysis. This one is the sine theta equal 0 means cosine theta plus minus 1. It's here. This is the same. Okay, Dirac and Majorana. Then we confirmed this velocity analysis consideration. We confirmed. You confirmed the DMCT confirmed by integrating this invisible neutrino part. Then it is come out. Okay. Now for the simple numerical shown purpose only, just in the paper we give all the details. Okay, but in order to show that this somewhat numerical result, we just simply sum. Okay, simple case. Neglect.
So now if you integrate over d sine theta, you recover DMCT.
No. Because we can measure the E mu. E mu is known things.
Right, but so when in 2-3 slides back, so when you said that you confirm the DMCT here.
Yes, this is only neutrino related unknown angle. This theta and d phi.
So what's the difference between this and the back-to-back mu?
Back-to-back cases now. This is generally unknown here because unknown these angles. Actually, you don't know this energy of anything, energy of neutrinos, anything. Not just the
So
theta n.
this is the integration over.
This is whole 5-dimensional. Whole 5-dimensional integrals. Neutrino related part is this one. Okay. And the other was change. We changed the momentum, the space for the using the only special kinematic reason.
So integrating out the theta and phi, you recover
DMCT. Yeah.
And then you don't integrate out the other stuff.
Yeah.
So shouldn't that include the back-to-back case as well?
No. This is different because we have to back-to-back case. We have to change all the complicated this intermingled because here E nu is there too. Okay, this is usual way, but in the case of back-to-back, E mu is measurable. Okay.
But anyway, I mean, this looks more general than back-to-back.
Sounds
Like including also back-to-back.
But this part is all intermingled with the E mu. Okay.
Yeah. Okay.
E mu and E nu actually. E mu and E nu are same actually. This that I don't show here. Just actually just the whole this variable transformation. I didn't show that. Okay. Okay, because good question. Next time when I show, I want to hear this variable exchange too.
So then accept this.
No. Because variable exchange is important too.
Okay.
Not just intermingled. Okay. And then the immune design theta like this way. Okay. Now this is the as I already showed this one. And this is the page which I just start, okay? Now, simple case, neglect muon and neutron mass. If you actually ignore muon mass, because muon mass is not very small, but if then resonance contribution almost disappearing, okay? D goes to mu nu is not possible, okay? So this is, we just remove just the resonance contributions. And as I mentioned, there are 3 form factors, and then I just choose only dominant one, okay? FA. And as the form factor is constant, okay, usually they're varying, but we don't know yet the exact form factors, okay? This has not been calculated. So we just going to use this as a kind of function and put outside as a kind of constant like this, the result. Okay, then this is the back-to-back case, this Dirac case, minor case. It's quite similar. The E mu is the energy, K mu is the kinetic energy, or muons. And E mu and K mu is actually very same actually in the approximately, because the average-wise E mu is very large, something like 1.6 GeV, and M mu is some 0.1 MeV on the GeV. So this is so small, so we can say K mu and E mu is almost same. Then this one minus cosine, which I already got it. Okay, like approximately like this way, which was we get this one by just the Hellas consideration. They actually M over E was something we ignore that. So this was kind of thing. Okay, we ignore this part, then come out exactly same thing. But more correct is E mu minus K mu cosine theta. E mu square plus K mu cosine theta like this. Okay, this distribution is this way. The two-dimensional E mu is like this way. Theta is like this way. It should show. Okay, I mean I already did show this one some time ago. So this is the angular distribution. This is the energy distribution, which I already said that. Oh, because of this one, this because almost zero. E mu K mu is actually almost same as I mentioned, okay? Then this is E mu squared. 10 minus 3 pi. That is almost zero actually, okay? So this is 10. This makes actually large difference in branch voltage. It's about 20 times large difference. This is measurable quantities. Okay? So at the end of the discussions, okay? Branching fraction of this one coming in back to back. With the total branching, the ratio, the rate of this gamma width, and then comes out 10 to minus 12 or 10 to minus 11, which means actually very small. Okay. Presently, as I mentioned, we have something like designed luminosity. I'm saying, okay. Still, this bell doesn't achieve their designed luminosity, but assuming they will achieve designed luminosity, then they are going to have 10 to 11, 10 to 12 Bs, total Bs. And then we need actually fully reconstructed Bs because we don't have a rest frame of B. The other must be fully reconstructed, which makes about 100 times decreasing this total weight, which means at the end, they are going to have about 10 to 10 or something around there, okay? So now we have like this,
So excuse me, the branching ratio is dimensionless.
Because I have this FA.
FA, what's FA?
FA is form factors.
And then, I mean, so it's just in numbers, so what?
It's the numbers, but the scale of the GeV.
So FA, what's the number? What's the value of FA?
FA could be something usually varying, okay, between 1 and like this way. That's the usual the form factors. There could be, let's say, 0.5.
A typical value,
Yeah.
0.5 GeV.
Yeah. Something like that.
So basically the branching fraction is around 10 to minus 12.
Yeah. But this is the only for this B0 case. I need the B0 bar. Okay, B0 bar is also giving exactly the same things. Not only that, we can do the electrons too. We did only muons. Okay, so I mean muon is, I mentioned muon is the best to experimentally measure. But why not electron? If their number is so large, then they can do electrons too. Okay, but usually they have uncertainty larger. But let's assume we just brute force. Then we got the fourfold. Okay, so we got this is something about 10 to 10. Okay, so that is just touching this designed luminosity. Okay,
In
so
bell 2?
pardon?
In bell 2?
Yeah, very true.
So
Designed luminosity.
So you need 10 to 10 Bs.
Yeah.
B and B bar.
More than that. In order to have a
10 At least they are 10 to say 8. 10 to 9 maybe.
Yeah. They have now design luminosity, they say about 10 to 12 Bs, okay? But fully reconstruct this bring down 10 to 9 or 10, 10, okay? So this is, they are just touching. But probably future, if they have they do it, they can do it better. Okay. I mean, futuristic, okay. I mean, I don't need to worry about future, okay. This present is also important, okay. Background, okay. Background is like they could come in tau decay like this. But usually, mu and more neutrinos, okay, not just 2 neutrinos, okay. 2 neutrinos, which we draw diagrams like 2, like double, like weak charge current, okay. More than that is like they have something much more like a vortex. So they must have a much smaller branching fractions, this one, okay. So I probably theoretically background is not that severe, but experimental background, that could be, I don't know, because that you have to B0 by vector like this way, and then there must be missing, that could be very difficult, okay? So that depends on experimentalist. But this can be many ways they extend, okay? This can go to J psi, it goes to psi 1s, 2s, Higgs decay to like this way, K0. There are many these possibilities, okay? So once this is fully now, people think this is correct, and this is very important, they're going to do not just simply one, they're going to do whole this many ways, then adding up all, then they got the, possibly they can see the difference. Okay, now, very important, which I want to say is that J psi and epsilon 1s. J psi is the best 3. The best 3, they have about 10 to 11 J psi's. Okay? Now J psi to mu, nu. This case, epsilon 1s is the best they can do it. Epsilon, the best is epsilon 4s. Okay? They have a slight larger energy, but much less the cross sections. So if the 1s, they have a much larger cross sections. Now, they just reduce the energy means they're easy to do it. Increasing energy is difficult, but reduce the energy is not that difficult, they say. So they can do this one too. Now, let's see the only J psi case, because they are very similar. Okay? J psi is going to gamma to the mu, and to the this way. You can neutral current, or this gamma double and doubly charged current like this way. Okay? There are 2 possibilities. Now, presently, V0 to mu is very small. Wow, then they say, this is impossible. There's difference. Because V0 mu and J psi mu is totally different. V0 mu is like efficient, fluctuating neutral current. Okay? This is penguin diagram, actually. Penguin, not usual penguins. The penguin in the penguin annihilation, such a penguin diagram. Okay? Photonic penguins annihilation diagram. So this is so small. But J psi to mu is so large because this is possible, a standard model. This is standard model, truly level impossible. We have to do it so difficult. So this one is different. This is weak, double weak charge current interaction. Okay, so this is totally different. People say, so small, this must be so small. No. This is almost impossible to do it. Because of that.
You mean the branching fraction is what? So a bit smaller than 10 to minus 10.
Oh, I mean, this one, if we do it, this one is Malajan. I said back-to-back case.
Yeah, I mean, so you said it's about 10 to minus 11.
10 to minus 10 if we add up this 4-fold.
Then it's good. I mean, basically, the B to mu would be background. So,
Uh-huh. Yeah.
it's even better than J psi. J
Yes,
psi
yes.
is too much mu.
Yeah.
Background.
It's very smart. Yes.
But you said J psi must be better.
Oh, no. Because I won't have a large number of events, then this is it.
No, the background is large, so the signal is
Yeah. But still, they have much larger event numbers.
which is useless for you.
Okay, one is the mu like this way, large across the event rate. Okay, so now then let's go to the slight bit, go on the next page. Let's do the same. It's very simple. This is not fully the consideration. Very simple Laplace consideration. Okay, and then this case, J-precise vector can be polarized. Okay, so let's do the polarization direction as the mu direction like this way, or J-precise to one, the option 1s2. And then I can do the very similar this Helsinki analysis. Okay, then coming out the Dirac case and Majorana case is different classical distributions. Okay, so you can see the difference too here too. Okay, J-precise 2, option 1s2. There are many ways you can do it. Okay, so at the end, this is conclusion I'm saying. Further discussion was not much discussion. Okay, Compact already asked that. Collinear case there is possible, but this is very small because endpoint of phase space. PDMCT I discussed a lot, and neutral mass generation mechanism doesn't matter to me. Neutral mass is there, then this is possible. Okay. Scale dependence, mixed method PMNS. I didn't do a very perfect the PDMS. Okay, but if we do the calculation, you can put there too. Phase space no symmetry forbid this. Okay, so this is all possible. Okay, now summary. We consider B0 decay, B0 to mu mu nu nu. Implementing the Fermi-Dirac static to find the difference between Dirac and minor neutrino and test the practical DMCT. Okay, that is very important because people, whenever I talk, kind of some solid rocks, they just said instantly, well, wrong, because this must be amnuscated. Everybody say that. Okay, I never met anyone just before I say accepted. They just said no, no, no. Then I explained one by one. They say at the end they accepted. Okay, this exactly same thing happened on Paris. Okay. Special kinematic configuration vector muons in the Bill rest frame. There is a striking difference between D and M, which does not depend on neutral mass. Okay, so you can overcome this DMCT. We give full details analysis, including everything actually. Neutral mass depends on. We never put the neutral mass 0 there. Okay, we put every neutral mass there. At the end, numerically only. Okay, if non-zero neutron, the numeric part is there, at that we just ignore that. Okay, if this is 0, then this M scale there. We never ignore that. Finally, similar decay exam such as the others too. Okay, so my final comment conclusion is the neutron stability decay. Okay, has a limitation, as I mentioned. Because inherent limitation, because that is beyond standard model actually. Okay, delta L equal to beyond standard. That is, this one is standard model allowed decay. Okay? You don't need to worry about that at all. But people think just from the exactly they just educate from there, and then these two must be M square 2, they say. No, because origin is different. And there comes nu coming out, and you have to disappear. You are measuring that. Here, you measure, you don't need that because you don't see that you integrate, and you got this interference. You got like this way. Okay? Because you see the neutrinos, you don't need to go there. And this one is this standard model allowed things. Not like delta, this lepton number violating this neutron delta decays. Okay? So I think this is only viable alternative to this MBDM, this DB, like neutron stability decay. Okay? Neutron stability decay is also good, very important. Okay, we have to do it, but there's possibility. we never can measure it because so small neutron mass there. And another large uncertainty in the is practically this the nuclear matrix element. And this is actually standard model not allowed. This is standard model allowed, and this possible. So that's it. Okay, so this is the final. So people tried all this all the time. There's much larger area. You can do it. When I talked to this JF I have over China, they said, "Wow, maybe this can be useful for even for the heavy style neutrinos." Okay, because heavy style neutrinos they did always delta equal 2, lepton number 2 violation all the time. Okay? But heavy neutron neutron is actually the nucleus case. Okay, so nucleus is somehow you have to fix the models, then somehow slightly difficult the complication coming up.
Okay, thank you. Question? Okay, question? No?
So, does this mean that in the near future, we should be able to distinguish whether
I
neutrinos are
think
Dirac or Majorana?
it will take some time, I don't know, because experimentally,
But what are you waiting for?
as you discussed,
Yeah.
we just discussed.
That's pretty possible.
Presently, just fully, if they achieve the design luminosity, then they touch. Okay, then because in order to see this, because I didn't say about background, okay?
No, I understand.
In order to they do the background taking out, then the efficiency, like some corrections, they are coming out. At least they need a 10 times larger number event. Then they can do it. Okay.
Who is they? Bell 2 or?
Bell 2. And then now this BESS is trying to do it by using the J-psi, which I just showed last the transparency, which paper showing. That is using the J-psi. They have the good thing is there. They already have 10 to 11 J-psi. They just need analysis their data. So I said to them, the J-psi, you are the best, because the Bell 2 is they can do it by using epsilon 1s. Okay, epsilon 1s also possible because epsilon 1s they have much more number event. This production rate of epsilon 4s and epsilon 1s is about 100 times larger. Okay, epsilon 4 is much smaller this event rate. So if they bring to the epsilon 1s, but they have to change the energy. They have to do all this experimental tunings like this. So I mean that takes some time, but they can do it, I think, because the epsilon 1s case they have much larger number of that. Epsilon 1s, as I mentioned, to mu is about 2% branching fraction.
So you think this method will be able to give a definitive answer in the future?
I think so, in future.
How future? How long would you estimate?
Depending on how it's going.
100 years.
I don't think 100 years.
I mean, you push the Bell 2.
Yeah.
100 years is better than
Yeah, say
neutrino
100
study.
times more.
They will, because anyway, I mean, the important thing is kind of thing they want to have. I mean, I cannot do it because I'm not experimentalist. They say, oh, this is important. We have to do it. That's the important thing. Now, best is they want to have a Nobel Prize because they got this Nobel Prize. Because this, if neutrino is Dirac or minor, they know that, then that's it. But nothing else can be important for that than this.
Also, one more question. So your method is going on this flow chart.
Yeah.
Your method goes down, right?
Yeah.
And then the DMCT is if you integrate out the momentum of the neutrino. So that's to
Yes.
the right.
Yes.
But you have an extra direction. Is this process facilitated by any exotic non-standard interactions? And
Yeah.
You're claiming that this can avoid the DMCT.
No. Yes, also. I mean, in the case of even going that direction, if there's a new physics, then you can go this way. Okay,
So this
but
is not-
in my case, I don't need because
Yeah.
this is possible by standard model. Okay, fully allowed by standard model decay.
No, I understand.
Yeah, just a weak charged current.
But it is possible to avoid the DMCT and integrate over.
Yeah.
the neutrino moment.
Yeah. I don't need integrate.
No, I understand.
Yeah.
Okay, any other questions? Maybe from the Zoom? If not, let's thank the speaker one more time. maybe.
Thank
Okay,
you.
so yeah, we will have dinner together. 30 minutes at 6 in the lobby.
Lovely.
Yeah, now.